right, great. All right, so today we're going to actually start off with just a little revision on separating techniques. So we're going to do these questions and then we move on. All right, so we're looking at these simple questions and then we move on from separating techniques. All right, so let's go. So it says, think carefully about the following statements. Are they true or false? Underline your answer. So A, in filtration, the filtrate is always a pure liquid. What would that be? True or false? False. False. Yes, that's correct. All right, so it's hardly any case where it actually is pure when it is filtered. So it's always has a little bit of the residue in it, so it's not pure. All right, B, drinking water can only be obtained from seawater by distillation. So we're saying we only can get drinking water from seawater by doing distillation. True? Someone says true. False. 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 All right, so we have two possible answers given. All right, so let's look at it and see. So let's see if it's false, then that means there are other ways of getting pure water from drinking water from seawater. What other method do you think could be possible to get drinking water from seawater rather than distillation? Decantation? No, decantation will not work with this one because the salt is already dissolved in the water. So decantation will not be an option for this. Any other one that you think? See if we can eliminate. Oh, desalination.
Mommy, I need to plug in this.
All right, so desalination is removing the salt from a substance. All right, so if you remove salt from it, then that means we can go ahead and collect the water, right, from it. So that's true. So therefore, this statement would be false because we can use somehow desalination to get the water part. All right, so C now, the fractional distillation of miscible liquids is only possible if the liquids have different boiling points. So what's saying is that we only can separate miscible liquids if their boiling points are different during fractional distillation. All right, so we have one person saying true, true again. All right, so and that's true. For it to separate, they have to have a slight difference in their boiling point. All right, D, paper chromatography is a physical method for separating mixtures. What do you have there? Someone has true or false. All right, so one person has false. I think that's false. True. Another person has true. All right, so false. All right, so let's examine the question. So paper chromatography, it is used for separating mixtures. All right, so that's a true statement there. But is it a physical method? All right, so physical methods would basically are the things that you can manipulate in order for you to get the separation, right? And which we do actually manipulate paper chromatography in order to get them separated. So it is actually a true statement, right? So all our separating techniques that we did last class were actually physical methods. All right, last one, mixtures have fixed melting and boiling points.
Huh?
So what do we have for that one? Fixed melting and boiling point. False. One person says. False. False. All right, great. So we got that one. right? Because remember, mixtures can be different based on the proportion in which you mix it with. All right, so question 2. So we need to name the separating techniques usable that's suitable for each of the following mixtures. So A, to obtain drinking water from muddy water. So which technique could we use to get drinking water from muddy water? All right, someone has filtration, no other options. All right, so let's examine and see if filtration can be possible. So the important part here says drinking water. So that means if we're supposed to filter muddy water, we're supposed to be able to drink it safely of the filtrate. So remember the first question here that says filtration always produces a pure liquid, and we say false, right? So if we actually filter muddy water, some of the mud will actually pass through the filter paper. So it's not pure water that you will actually receive for you to drink. So the only possible option there would be distillation, and specifically simple distillation. So simple distillation will only evaporate the pure water so it can actually condense for you to get to drink. So that's the best option to get pure water from muddy water. All right. And second one, to separate petrol from crude oil. All right. So that's a familiar one. So fractional distillation. All right. Next, to remove leaves from swimming pool. Filtration. That's correct. Next, to obtain pure sugar from a solution. So pure sugar from solution, evaporation,
Crystallization.
and crystallization. All right, so we can just use crystallization because it will actually state that evaporation is needed as well. And finally, to determine whether the color in a fruit juice is a single substance or a mixture of colored substance. And that one, exactly. So paper chromatography. All right, so the last question, you are asked to separate a mixture of sand and table salt. All right, so some of your salts actually end up into some sand. Name the separating techniques needed to carry out this separation. Explain how you would carry out the procedure. All right, so what are the separating techniques that you use? Separate the sand from the table salt.
Filtration and crystallization.
So filtration and crystallization.
Yes.
All right, so how does the filtration comes in?
Well, first of all, you're going to need to add some sort of solvent, most likely water, to the mixture of salt and sand. When you do that, you're going to filter off the mixture between the salt and the water
Mm-hmm.
from the sand. That's separating the sand from the salty water. But
Okay.
in order to get the salt from the water, you're going to need to carry out the crystallization.
All right, great. All right, so I hope everyone got that. So we use filtration and crystallization. So we add water to the mixture. So the sand will not dissolve in the water, but the salt will dissolve in the water. So if we filter it, we'll get the salt water and the sand will remain. And then from the salt water, we can go ahead and heat it so we can get the crystals from your salt remaining after the water evaporates. All right, so that's it for a recap of our separating techniques. All right, so what we're going to do now is to actually look at, just to recap also some equations, chemical equations, before we move on to our periodic table. All right, so we're just going to take a short while to recap. The first, we're going to look at ionic compounds, just naming them, right? Just to ensure that we all know how to do these, because it's going to be important for when we're looking at moles. All right, so we're going to name the following compounds. All right, so you can go ahead and start giving me the names. So first one is CaO. CaO would be calcium oxide, great. All right, next is KBr. Potassium bromide, yes, and the third one is Al2O3. Aluminum oxide, great. And the last one is MgCl2. Magnesium chloride. All right, great. So those are just a good recap there. All right, so in this little table here, it's asking us what compounds would be formed when these ions combine. So if we have Na plus and Br minus combining, we will get
Sodium bromide.
so it's sodium bromide, and the formula would be
NaBr.
NaBr. All right, going across, Na plus S2 minus gives us
Sodium
sulfate.
and the formula is
Na2S.
Na2S. All right, and the next is Na and N3.
Sodium nitrate.
Sodium
Nitrate or nitrite? I don't really know.
Nitrate.
Nitrate.
What is N3 minus? Nitrate, nitrite, nitride. Which one?
Nitrate.
All right, so an ion is for elements, the ion form of each element always ends with "ide." Right, so because this is just N, it's an element, so it's just the nitride. Right, so in this case, it would be Na 3N. All right, last set. So aluminum now with these, so Al3 plus and Br minus gives us
aluminum bromide.
so aluminum bromide, which is Al
Br3.
Br3. And the next one would be
Aluminum
sulfide.
Aluminum sulfide, which is
Al2S3.
Al2S3. And the final one would be
Aluminum nitride.
Which is
ALN.
Al. Right. So that shows that everyone knows how to get our equations from our ions. Great. Right. So please remember once it's an element form of the ion, it always ends in "ide." Okay. All right. So let's see. So that the correct name for each Fe2S3 is
Iron
2
sulfide.
iron 2 sulfide or 3?
Iron 3 sulfide.
Iron 3.
Great. So iron 3 sulfide. And why do we use the 3 instead of the 2?
Because its charge was 3. What 3 plus?
How do we know which charge it was? The 2
Because
or
the
the 3?
charges are switched.
Okay, great. So the charges are switched. So that means whatever S is, that was a charge for Fe. So S is 3, so that means Fe was 3. So that's that. And then the next one is CuO.
Copper 2 oxide.
Copper 2 oxide.
Copper 2 oxide.
Copper 1 nitride, which one of these would it be?
Cu3N.
Cu3N, great. And lead 4 oxide would be?
PbO4. No, PbO2.
PbO2.
Simplify.
All right, last thing before we start doing something new is we're going to look at balancing chemical equations. All right, so we're just going to do some of these that are in these. All right, so how to balance chemical equations. All right, so let's go to the first one. All right, so you're just going to tell me the numbers that we need to balance them off.
The oxygen is unbalanced.
All right, so the oxygen is unbalanced, so we need to balance off the oxygen. Adding a 2 in front. All right, where would the 2 go?
In front of this CO gas.
So put the 2 in front of the CO gas here.
Yeah.
But that's not balanced yet.
And
So,
then in the product again, and what was produced in front of that another 2.
All right, great. So we have two C's here, 2 C's there, and we have 2 O's here plus 2 O's. That's 4 O's on the left, and 2 times 2 is 4. Great. So that's balance. All right, next one.
Placing a 2 in front of the product.
So 2 in front of the product. All right, so let's see. So we have 2 H's on the product side, 2 H's on the reactant side, 2 N's on the product, 2 N's on the reactant, 2 times 3, 6 O's on the product. We have 2 here and 5, so 6 on the reactant. So great. All right, so we're going to do 2 more and then that's it. So C and D. So C now. So put a 4 in front of the Cl, HCl. That's all. And a 2 in front of the Cl2. All right, let's see if this balance off. All right, so on this side we have 1 C. This side we have 1 C, so the C's are balanced. H, we have 4 here, and we have 4 H there, balance. All right, Cl we have 2 times 2, 4. We have 4 here and also 4 here, so that's 8. So we have 4 here and 8 over here. So this 2 needs to be replaced with a 4. With a 4. Right? So we have 4 times 2, 8. We have 4 and 4, 8. All right, and then the last one now. All right, let's do this one together. All right, so when I'm balancing equations, I do it a little bit longer until I can fully get it. All right, so since it's not an introductory class, I can just do it faster by we go in the order of from metals to non-metals. So we start balancing off the metals first. So the only metal here is aluminum, right? So on the reactant side is 4. On the product side, we only have 1. So that means we add a 4 here, so we balance off the aluminum. Right? Now the next one is we move to C. If there is any C, we move to a C because the C is not a metal or a non-metal. All right, so we balance off the C's. So we have 3 C's here. On the reactant side, the product side only has 1. So that means we put a 3 right here. So our C's are balanced. And then in between now, we look at our hydrogens, right? So hydrogen here is 4 times 3, which is 12. So we have 12 hydrogen there. And here we have 3 times 4, 12. So we have 24 hydrogen on the product side, and we only have 2 on the reactant. So that means we need to put a 12 here.
12.
So 12 times 2 is 24,
24.
right? So the only thing left is our oxygen to ensure it's balanced. So here we have 12 oxygen as well. So we still have 12 oxygen here. So 3 times 4, so that's 12 on our product side. And then on our reactant side, it's 12 times 1, which is 12. So therefore, it's balanced now.
Mm.
All right, so that's how I normally balance equations. Move from the metals, then hydrogen, then your non-metals. All right, so we should be able now to balance any equations that would be needed. All right, so now let's look at the periodic table and specifically the trends in our periodic table. All right, so we know our periodic table is arranged in terms of groups and periods. All right, so we know we have 18 groups and in total 17 periods, but we're only focusing on the first 20 elements for CSEC purposes. Right, so we know elements are placed into their respective groups based on a specific characteristics. Anyone knows that characteristics that they're placed in their groups based on? Their atomic number. All right, so is that actually the main characteristics why they're placed in their respective groups? Why do we have sodium in group 1 but magnesium in group 2? Not just because sodium is 11, magnesium is 12, so they flow in that same order. Why exactly is it in group 2?
In terms of groups,
in terms of
they're arranged by they're placed in groups because they have similar chemical characteristics,
right.
similar bonds. Yeah.
Well, yes, correct chemical characteristics, but Adrian has the answer I'm looking for. They're valence electrons, right? So they are in group 1, not just because they act together or the same in terms of chemical properties, but they actually have the same amount of electrons on their outer shell,
Outer shell, yeah.
right? So all group 1 elements has just 1 electrons on the outer shell, all group 2, and it continues like that, right? So that's the first thing you're supposed to know, why elements are placed in their groups, because they have the same amount of electrons on their outer shell. And that's the main reason why they behave the same way, because when they're in the same group, because of the amount of electrons, right? So how do we know why they're placed in periods now?
Because the amount of shells they have.
The amount of shells that they have, right? So groups because of the amount of electrons on the outer shell, periods because of the amount of shells that they have going across, right? So those things are important to know why they're placed like that. Now let's look. All right, so we already know the structure of the periodic table. All right, we know that it's grouped into periods and groups. All right, anyone know what the atomic radius is?
No, we can.
Like how big it is?
The size of the element.
The size of the
Element.
the size of the element or the atom. Right, so the radius because remember we draw the structures like a circle, right? So from the last shell to the center of the nucleus, that is your atomic radius. So that means if we look at going down each group, each time we're adding a new shell. So because we're adding a new shell, that means the radius is actually increasing, right? So that's what we'll be looking at in the next four, 4 point. All right, so the time is going to expire soon. So I'm going to actually break now and come back, and so we can start looking at each of these specifically. All right, so I'm going to close off now and resume. Let's look at our trends now in group 2 first. All right, so we know that group 2 elements are beryllium, magnesium, calcium, strontium, barium, and we see that they are in group 2 because their last shell has 2 electrons. All right, so we're going to actually ignore radium even though it's in group 2, and because it's radioactive, it's unstable. So unstable means that we're not able to predict exactly how it will react at a specific time, right? So all the elements has 2 electrons on their outer shell, which is noted, right? They must lose 2 electrons to become stable, right? So they all will have a +2 charge when they lose electrons. All right, so the elements are reducing agents. All right, so even though we haven't been there as yet, though that means that they will all lose electrons. There is an increase in the atomic radius down the group, and we can see why, because each time you're going down, you have more shells. So that means your radius will increase. All right, so this gives us some physical characteristics of each element. So we notice from magnesium going down to barium, their atomic radius or radii increases. Your ionization energy, it decreases. So let's look at the ionization energy. What exactly is this ionization energy? All right, so anyone can fill me in with that. What is
That is
ionization?
the
Go ahead.
energy needed to remove an electron from an ion or atom.
All right, great. So it's the amount of energy that's needed for these elements to actually lose their electrons to become stable. So the question is now, why going down the group, we need less energy to actually make them become ion? Why does magnesium needs more energy than barium?
Look, you made me happier than I've been.
Because of the distance of the electrons from the nucleus.
So what does the distance has to do with the energy that's needed?
That the further the electrons are from the nucleus, the smaller the attraction to the nucleus and the lower the energy needed to remove
Great.
the outer electrons.
Very good. Right? So the further you are from the nucleus or the electrons, the less the attraction between the protons and your electrons. Right? So because the attraction is less, then that means our electrons need less energy to actually take it off the atom when the atoms get bigger. Right? But we see there that strontium actually behaves differently in terms of strontium and barium, right? And we're going to look why based on their electronic configuration. So if we look at strontium electronic configuration, this is where it starts to include the 18 because of its atomic number. So barium has 2 18, strontium has 1. So the reason why strontium needs less energy than barium, even though strontium is above barium in the periodic table, is because of the the amount of electrons that's present on the fourth shell. All right, so the amount of electrons on the fourth shell causes that variation in strontium and barium. That's the only variation there. All right, but you don't need to actually go fully in depth with that. All right, melting point. So we notice going down the group, the melting point reduces, right? And that would be the same, right? Just like the same explanation, because melting point, going down the group, right? What would be the reason why it's going to be easier to melt?
Because there will be less energy required for the element to melt. The
Yes.
electrons will be released easier.
Yeah, so because of the atomic radius, the electrons will be released easier, so it takes less energy to get it melt. And going down density, going down the group, the density increases. And we should know why the density increase. But why does the density increase? Because the radii increases. Not just because the radii increase, but there is one specific reason based on density. If you do physics, then try to relate it back to the equation for density. So we know density is mass over volume. What specifically is changes between magnesium to barium, why the densities would increase? Because they're getting bigger, so getting bigger means what? Mass is increased, great.
Mass.
Exactly. So it increases in mass when you go down the group, right? So therefore, their densities will actually increase. All right, so other things to note, the compounds form conduct electricity when molten and dissolved because they are ionic compounds. So that's saying that when group 2 elements react with nonmetals, they form ionic compounds that will be able to conduct electricity. The oxides and hydroxides of group 2 elements are basic, right? So they are bases. So calcium oxide or calcium hydroxide, those are basic substances, and they react with acids to give us salt and water, right? So that's very important to remember. So the oxides and hydroxides of group 2 elements, they form basic solutions. All right, so solubility of oxides and hydroxide increases down the group. With all other salts, the solubility decreases down the group, right? So going down from beryllium to strontium, their solubility of their oxides and hydroxide increases. So beryllium oxide is less soluble than strontium oxide, right? And that's or dependent on how their reactivity somehow. So all chlorides of group 2 elements are soluble. All right, so let's look at the reaction with certain things. So reactions with water, dilute hydrochloric acid, and oxygen. So first one is magnesium. So magnesium reacts very slowly with cold water and vigorously with steam, forming magnesium oxide and hydrogen. So if we have cold water with magnesium, it's going to have a very slow reaction. Or if you have steam, meaning you're just heating the water, then magnesium will be a vigorous one, producing magnesium oxide and hydrogen gas. When it's reacting with hydrochloric acid, dilute hydrochloric acid, it's a rapid reaction, meaning it happens fast, and we get magnesium chloride and hydrogen gas. And with oxygen, in air, the layer of oxide forms, preventing further oxidation, a brilliant flame to produce magnesium oxide. So it's basically saying that when magnesium reacts with oxygen, it forms the oxide layer, which prevents it from corroding. right? And then calcium now. Calcium reacts vigorously with cold water at first, but slows down sparingly. Soluble oxide, hydroxide is formed. Hydrogen gas is also formed. So with calcium, it starts off vigorously with cold water, and then as time progresses, it starts to get slower and slower. With dilute hydrochloric acid, it's very rapid with dilute acids. And we get the chloride, the salt, calcium chloride is formed, and hydrogen is also formed. Reacted with oxygen, forms a layer of the oxide, prevent it from corroding, right? Strontium. The strontium vigorously with cold water, forms a hydroxide and hydrogen gas. With the dilute acid, it's violent. It produces chloride and hydrogen gas, and it's a vigorous reaction with oxygen. And then finally, barium. Barium is very vigorous with cold water. Hydroxides are formed with hydrogen gas. It's violent reaction with dilute hydrochloric acid, and it's a vigorous reaction with oxygen. So we notice that going down the group for reaction with water, it's very slow with cold water, right? So it moves from very slow with cold water to very vigorous with cold water, right? With acids, it's a rapid reaction, and then going down the group, it gets to violent, right? And with oxides, the same. So it starts soft, like a very smooth reaction starting off, and then going down the group, it gets a vigorous reaction producing the oxides. So those are important. So remember. All right, so these are the equations of some of the elements being used. So calcium reacting with oxygen gives us our calcium oxide, right? Reaction with water, magnesium reacting with water give us magnesium oxide and hydrogen gas. That's when it's in steam, so we notice it's gas of water there. And then when it's liquid cold water, then it produces magnesium hydroxide and hydrogen gas. So that's important to know that magnesium with the steam produces magnesium oxide, magnesium with liquid water produces magnesium hydroxide. Calcium with liquid water would produce calcium hydroxide, right? And then we know metal and acid gives us a salt and hydrogen gas. All right, so we've been through the ionization energy. All right, so now let's look at group 7 or group 17. All right, so we notice they all end in 7. So they all have 7 on their shells, last shells, right? So they all will have an oxidation state of -1 or 1 minus because they all need 1 electrons in order to become stable. So we're going to look now at a term that's known as electronegativity. All right, so let's go. What does electronegativity means?
It's the tendency of an element to gain an electron and become negative.
All right, so the tendency to gain electron to become stable and become a negative ion, right? So we note here for in group 7 elements, the electronegativity decreases going down the group as the ability of atoms to form negative ions decreases. Why? So why going down the group, the tendency to form ions decreases?
Because it will be more difficult to add an electron if the atom is larger. It will be more difficult for the atom to gain an electron if it is larger.
All right, so why, if it's larger, would it be hard for it to actually gain the electron? What's a key factor in order for it to gain electrons? Yes, to get a full outer shell. All right, so that's not. All right, so yes, so the key factor is to get a full outer shell, which is to get 8, right? But in order for non-metals, not just group 7, but any non-metal to actually attract electrons, there has to be an attractive force. Where does that attractive force come from? So where does the attractive force that non-metals need in order for it to actually attract electrons from metals? Where does that force come from? From the nucleus. All right. So the attractive force comes from the nucleus. So therefore, why does, when, as we know, that the atoms get bigger, it has the least tendency to actually attract the electrons to become electronegative.
Because the valence electrons become more shielded from the positive nucleus.
Great. Right? So the further you're getting away, that means the last electrons are getting less attraction from your nucleus. So that means they're shielded. Right? So because of that shielding from the previous shells, it's going to be hard for those atoms to actually get that attractive power to attract electrons onto their shell. So that's why going down the group, because the atoms getting bigger, more shielding effect, they have a smaller tendency to become ions, right? So a thing also to note is that the most electronegative element present is fluorine, right? So that's something to note, that the most electronegative element there is fluorine. All right, so let's look at some factors here, or properties. So we're looking at fluorine, chlorine, bromine, and iodine from group 7. So their physical state at room temperature, all are fluorine and chlorine are gases at room temperature, bromine is a liquid, and iodine is a solid. Right? Their colors, it's good to know their colors. Fluorine is a pale yellow, chlorine is a pale green, bromine is a brownish, reddish brown, sorry, and iodine is a black. So we notice their radii increases because they're going down the group. And we have been through that. We also been through their electronegativity. It goes down as they're going down the group. Their melting point, right? It actually between fluorine and chlorine, is that a drop in melting point or a rise in melting point between fluorine and chlorine?
Sorry, repeat that.
Between fluorine and chlorine, is that an increase in melting point or a decrease?
Increase.
Increase? Great.
Yes.
All right, so increase in melting point. And the density, we note, is actually increasing as we going down the group, and we already know it's the same explanation as our group 2 elements. All right, and we also know that group 7 elements are known as halogens. So these elements are diatomic, and diatomic means?
They have 2 hydrogen ions on it.
Repeat that, please.
They have 2 hydrogen ions.
They have 2 atoms.
I mean, some about 2.
Yeah, so
They are bonded with each other.
yes, so 2 of those atoms are bonded together, right? So because most of them are gases, so most nonmetals are gases in nature, so they just bond 2 atoms of each together to exist in nature. So fluorine as a gas is F2, chlorine as a gas is Cl2, bromine as a gas Br2, iodine as a gas is I2. So the melting point decreases as we look at that. We looked at the electronegativity. All right, so we look at the reactions between. So going down the group, they become more reactive. So it becomes less reactive, sorry. All right, so going down the group, we become less reactive. And why is it that we become less reactive? Yes, why is it less reactive when we go down the group in group 7?
Because the ease of ionization decreases.
Great. So it gets hard to make and become an ion, so therefore they are lesser to react. All right, so based on that, then we should note their displacement is that if you're below, so if we have chlorine and bromine in a reaction, chlorine will displace bromine, but bromine cannot displace chlorine because it's less reactive. So if you look at this example where we have chlorine, it's going to react with KBr, right? So that means, so K goes with Cl and Br goes by itself, right? So that's, so we know that halogens are ionizing or oxidizing agents, right? So the halogens oxidizing agent, and we know group 2 elements are reducing agents, right? So let's look at the last thing for periodic table, which will be our group, our period 3 trends. All right, so looking at period 3. So as we move from left to right of the periodic table, the physical properties of the elements change. So in some instances, the change is marked, and in other, there is gradual change. All right, so these are the elements present in period 3 of the periodic table. We note that all has 3 electrons on their structure. Right? But we know that if we look at sodium, which is from the left side, it is a soft metal, it has low density, and it's very reactive. Then magnesium is beside it, it is a harder metal than sodium, it has a low density, it's less reactive than sodium. Aluminum is harder than magnesium, it has low density as well, it's less reactive than magnesium. Silicon is brittle, it's a non-metal, not very reactive. Phosphorus is non-metal, low melting point, white solid, and it's a reactive. Sulfur is non-metal, low melting point, yellow solid, moderately reactive. Chlorine, non-metal, is a green gas, it's extremely reactive. Argon is a non-metal, it's a colorless gas, and it's non-reactive. So we notice between your metals, from sodium to aluminum, from left to right, it starts off with a solid, it's soft, gradually becoming hard. All are low density, right? And then it starts off with very reactive and moves to less reactive, right? And then we move to the non-metal sides that shows that it starts being a solid, off by being solids, right? Silicon, potassium, sulfur, solids, and then chlorine, argon, or gases, right? It starts off by being not very reactive, then it moves to slightly reactive, moderate, and then extremely reactive. And then we know that argon, because it's in group 8, it is non-reactive because it's already full, right? Now, if we look at the structures as they exist in nature, because sodium to aluminum are metals, they will exist, their structures will be of metallic bonding, right? Silicon would be a giant covalent. Giant means it has a structure looking like diamond or graphite, right? And then simple covalent, from potassium to argon, mean that they exist like S2Cl2 and such, right? Their atomic radii, we notice from left to right, the radii actually decreases, so it gets smaller. Question, why does the radius decreases when we go from left to right of the period? What's so
Because
unique?
their nucleus gets bigger.
No, but all right, so from left to right, the nucleus gets bigger, but here we're saying that the atomic radius gets smaller. So why is that the case? force of attraction decreases. Great. So the attractive force between these will be lesser going from left to right. So that's the main reason why the radii actually decreases. So the radii is not totally dependent on the amount of shells, right? Because remember, all these elements have the same amount of shells, right? And it's not because the increase in the electron amount as well, but it also has to do with the attraction between the nucleus and your last shell that would cause the radii to increase or decrease, right? So more attraction between your last shell and your nucleus will get a bigger radii in this case. Or the electronegativity from left to right, we see that it increases, which we know, right, should be the case. Your melting point actually increases from left to right for your metals and non-metals as well. Your boiling point increases as well. Your density, for your metal, it fluctuates as we looked at previously, and electrical conductivity, they decrease going across, right? So we know that our metals are the best conductors. So going across from more metals are going to reduce their conductivity property. All right, so we know those electronic arrangements. We know how much electrons they will lose or gain. Their state at room temperature, we did that. And if they're metals or non-metals, we know that as well. All right, so we just did all those and we looked at those. All right, so we did answer question 1 at the start. In what order are elements arranged in the periodic table? And someone gave based on their atomic numbers. What name is given to the vertical column of elements in the periodic table? All right, what's the answer? The vertical columns are known as groups, yes. What name is given to the horizontal rows?
Periods.
The periods. In which group does the element potassium belong?
Group 1.
Group 1. In which period does the element arsenic belong? Let's look. All right, so this is the periodic table. Arsenic is AS, which is right here. So that's arsenic. What period does it belong?
Period 4.
5.
4.
5,
No,
4,
4.
Yes, 4. In which group does titanium belong? And state whether these are metals or non-metal. All right, so let's look at titanium. So which says group? Yes, which group does titanium belong? Titanium is Ti, which is 2 away from calcium. So what group is that? Group 2? No, not group 2.
It's a transition metal.
So it's a transitional metal, right? But just to highlight, even though it's not changing the syllabus as yet, so the next update of the syllabus will have that this order that we have for groups are no longer existing. So the IUPAC, which is the institution for construction of elements in your periodic table, they have, I think, 1 to 2 years ago, has actually revised your periodic table to start from 1 and go right to 18, because we have 18 groups. So previously we had just 1, 2, and then we skip the transitional elements and say 3, 4, 5, 6 to 8, right? But now they have just started from 1, 2, and continue across until you get 18. right? So that's something to note, especially if you're going to do chemistry at university level. Right, so transitional elements, they will have their groups as well. So because titanium would be 2 away from calcium, it would be in group 4 in that case. Right, but not for CXC as yet because they haven't revised that aspect of the syllabus. All right, so state whether these are metals or non-metals. Cesium. All right, let's go back to the table and find cesium, which is CS. Is it here? All right, so
It's a metal.
it's not
Group
here. Let me
one,
see.
it's a metal.
It's in group 1.
Yes, sir.
All right, so it is a metal.
Metal.
Yeah, it will be right below potassium. All right, next is calcium. Calcium is
Metal.
the metal. Group 2, boron.
Non-metal.
Why is it a non-metal?
It can be both.
What
It is
group
a
is it?
metalloid.
What
Group
group is
3.
it? Group 3?
Yes, sir.
Aluminum is in what group?
Group 3.
Exactly. So aluminum is classified as a
Metal.
so boron would be a metal as well. Silicon,
Metalloid.
a metalloid.
Metalloid.
Right. Phosphorus,
Non-metal.
non-metal. Selenium,
Non-metal.
non-metal. And iodine, which is in group 7, is
Non-metal.
the non-metal. All right, so last one, statewide potassium. We're not going to do that because that also has changed. All right, so this is just extra things. All right, so I'm going to restart now. When we come back, we're going to start moles. Right, so we're going to actually start looking at some calculations and look at some moles calculations and see how far we can go. All right. All right, so let's go. So we're looking at moles. All right, so this time we're going to work some calculations. All right, so before we look at some calculations, let's define some specific terms. So exactly, first one is, what is a mole?
It is the standard term used to represent the amount of substance that contains 6.02 times 10 to the 23rd power.
Great. So amount of particle in a substance, yes, which contains 6.02 times 10 to the 23. Great. All right, so that's first one. Next is the molar mass. How do we define molar mass? The mass of 1 mole of a substance. Great. So molar mass is the mass of 1 mole of a substance. So those are the two terms that we're going to focus on for today's class. Let's see. All right, so let's look at how do we find the molar mass of a substance, right? So let's say we have, let's use sodium chloride. How do we find the molar mass of sodium chloride? Because as it exists here, this is just 1 mole of sodium chloride, right? So how do we know the mass that is present in 1 mole of sodium chloride, which is your molar mass? How do we find that?
By adding their mass numbers.
By adding their individual masses, right? So
Yes,
we know
sir.
that sodium has a mass of 23, chlorine has a mass of 35.5. So when we add those, we get 58.5 grams per mole. So another thing to note is that the unit of molar mass is gram per mole, because it's the amount of mass in 1 mole of a substance. Right, so that's how you find the atomic mass, the molar mass, sorry, of your compound. All right, so I'm just going to give you 2 for you to do right now, just to ensure that you fully understand as well. All right, so here we go. All right, so let me give you the masses of each. All right, so I'm seeing 2 persons' answers. Just waiting on some more. All right, so let's see if we get those answers. All right, so first one is calcium phosphate. All right, so we notice we have 3 calcium here, so we multiply 40 by 3. P here, it's 2P, so multiply the 31 by 2. And oxygen is 4 times 2, which is 4 twos, 8. Right? So in this case, it's 120, this is 62, and this here is 128. So when you add those, 248, 310. And that's what, yes, I'm seeing that's what most persons, or what everyone got. Right? So we get 310 for the calcium phosphate. And then for lithium oxide, all right, so lithium is 2 lithium, so it's 2 times 7, and then we have 1 oxygen, which is 16. So that is 16 plus 14, which is 30. And remember the units, gram per mole. All right, so those were easy, and it doesn't get harder than that. So finding the molar mass is just ensuring that you identify how many or how much of each atom is present and multiply it by its mass number. Right? So we have 3 calcium here, we multiply the 40 by 3. We have P times 2, which is 2, so 31 times 2. We have 4 times 2, which is 8, so multiply 16 by 8. All right, everyone got that? All right, so now let's move on to the good part. All right, so I like using the first knowing the equations for moles, right? So let's identify some of the equations that we're going to look at, right? So first, we have equation 1 that tells us that mole is equal to the mass of the substance divided by your
Molar mass.
molar mass, right? So that's 1. So let's say we have, instead of mass, we have the amount of particles or the amount of molecules or the amount of atoms. How can we use those to find mole?
Divided by Avogadro's number.
So we have mole is equal to number of particles or molecules or atoms, and that's divided by
Avogadro's number.
Avogadro's number, which is 6.02 times 10 to the 23. Right, so that's another equation. Our next one is, what if we want to find the mole of gases? So what's that equation if it's gas? In terms of the volume of gas that we have, how do we find mole from that?
It's the given volume of gas over the molar volume.
So mass, the mole is equal to the volume over the
Molar
volume,
volume.
molar volume, which is the volume at RTP or
STP.
Right? And we know these values, these RTP and STP have a set value. So it says that 1 mole of any gas at RTP has a volume of
24 dm cubed.
24 dm cubed. Right? And if we want to change it to cm cube, how much would it be?
24,000 cm cubed.
24,000 cm. Right? And if we have 1 mole of any gas at STP, then it will occupy a volume of
22.4 dm cube.
22.4 dm cube. And in centimeter cube is 2 to 400 centimeter cube. Right? So for today, we're just going to focus on these three to master them first, and then next class we look at the other, which involves concentration. All right, so let's go. All right, so we're going to look at a question that says, calculate the number of moles in 20 grams of argon gas, B 42.15 grams of magnesium carbonate. All right, so that's question 1. So let's go. How would we go about doing this? So we need to find the amount of moles in 20 grams of argon gas and 42.15 grams of magnesium carbonate. So what's the first thing we do? Let's start with part A.
So we're going to divide the mass by its molar mass.
So divide the mass by the molar mass. So that means the first thing we're going to write the equation. So we know mole is equal to mass because we're given a mass over the molar mass. Right? So now we need to know what the molar mass is. So in order to know what the molar mass is, we have to know what's the formula of the substance given. And what would be the formula of argon gas? Yes, what would we use for the formula of argon gas?
AR.
AR. Why not AR2?
Because it's in group 8, not group 7.
Because it's in group 8. That's the answer. So it's in group 8. So that means it's not reactive. So it will never react, not even with itself to bond. So therefore, argon gas is just AR. And the mass of argon is 40. Alright, so therefore we can find the mole, which is the mass given, 20, over the molar mass, which is 40. So we get 0.5 mole. Right? So that's it for A. And then for B, because we're given mass again and the substance, it's the same formula. The mole is equal to mass over molar mass. So again, we need to know what's the formula of the compound magnesium carbonate. What's the formula of magnesium carbonate?
Mg open bracket CO3 close bracket 2.
No, not quite. You're somewhere there.
MgCO3.
MgCO3. Remember, carbonate has a 2 as its charge as well, and magnesium has 2, so they both cancel each other out. All right, so that's our formula. So therefore, we find the mass, the molar mass. So magnesium has a mass of 24. It's just one of it, so it's just 24. Plus carbon, which is just 1, which is 12. Plus 3 oxygen. Oxygen here is 16 times 3. So this is 48, 16, so 84 gram per mole. Right, so the mole here would be 42.15 over 84, and we get 0.0
0.502. 02.
Right, so with these questions, it's very easy because once you identify what is given, we identify the equation. So because we're given mass for both, we use that mole is equal to mass over molar mass, right? And the next aim is to get our molar mass. Because we're not given the equations, we have to write the equations, then get our molar masses, then divide by the given mass to get our mole, right? So I'm going to share this worksheet with you, and you can do some, and let's compare some answers and see if we understand using these. All right, so I did question 1. So you're going to do question 2, 3, and 4. So as soon as you get your answers, you can just write them in the chat so we can all see the mass. Wow, that's a big number for question 3. Answer for question 3. All right, giving you 3 more minutes and then we'll go through together. All right, so let's see. We've seen some answers there. Let's see if those are indeed right. All right, so let's go. So question 2, calculate the number of atoms in 1.5 mole of HCl. So number of atoms, so that means the only equation that has that number of atoms is mole is equal to number of atoms divided by Avogadro's number, 6.02 times 10 to the 23, right? So we are given mole and we need to find number of atoms. So we make number of atoms the subject, which is equal to mole times 6.02 times 10 to the 23. So the mole is 1.5 multiplied by 6.02 times 10 to the 23. And that would be, I see someone has 9.0 times 10 to the 23. Alright, so that's question 2. So multiply the mole by Avogadro's number and we get the amount of atoms present. Alright, question 3. Calculate the mass of 1.5 times 10 to the 23 formula units of magnesium sulfate. Alright, so in that case, we're given the amount of particles in magnesium sulfate. So again, we will use this equation, right? So we're given the amount of molecule or particles or atoms, right? We need to first find the mole before we can find the mass. Because remember, mole is equal to mass over molar mass. So we first have to find the mole first. So the mole is equal to the number of particles, which is 1.5 times 10 to the 23, divided by 6.02 times 10 to the 23. All right, guys, when you divide that, what did you get for your mole?
0.25.
So you get 0.25 mole. So now we have the mole, we can find the mass. So mass is equal to mole times molar mass. So the mole is 0.25 times the molar mass. The compound is magnesium sulfate. So magnesium is 24 plus sulfur, which is 32, plus 16 times 4 oxygen.
It's 120.
So we get 120 gram per mole. And so multiply this by 120 and we get
30 grams.
30 grams. So the mass of magnesium sulfate that has that amount of particles is 30 grams. All right, and finally, calculate the number of molecules in 34 grams of ammonia. So it's basically we're working the opposite direction now for this question. So first we have to find, so we're still using these two equations, right? So we're given mass, so we have to use the mass one first. So mole is equal to mass over molar mass. So the mass is 34 over the molar mass. The molar mass of ammonia is NH3, where N is 14, H is 3 times 1. So we get 17 gram per mole. So we divide this by 17 and we get 2 mole. Right? So we have the mole, but we need the amount of molecules, which is we use this. So number of molecule would be equal to mole times Avogadro's number, 6.02 times 10 to the 23, which is 2 times 6.02 times 10 to the 23, which is 1.204 times 10 to the 24.
Yes, sir.
To the 24 molecules. Right? And I think that's what persons have great. Alright, so that's just using the formulas just as how they are to find the specific answers. Alright, so for next class we'll be looking at using these formulas as well as others in terms of when it's a chemical reaction. So these are just when it's just one specific substance. So what's going to happen if we have different compounds reacting together in a chemical reaction? We're going to look at those instances next class. All right, so that's it for today, guys. And thank you for tuning in today and see you guys next time. All right, the channel is Physics Force. All right, give me a moment and I'll send you the direct link to the channel. All right, so you can look at the channel. It also has other videos on topics that we will do or we have done before. And remember, each lesson now posts on the channel as well. All right, so see you guys next time.
All right, thank you, sir.
Thank you, sir.
No problem.